Atoms and elements. So in this lecture, we're going to learn a little bit about the building blocks of matter. So those are atoms. Dalton's atomic theory is summarized in 5 postulates. First one, matter is composed of exceedingly small particles called atoms. An atom is the smallest unit of an element that can participate in a chemical change. As the course gets going and as we talk about next week's topics and eventually we'll get into chemical reactions, you'll see exactly what we're talking about and that will make complete sense. An element consists of only one type of atom, which has a mass that is characteristic of the element and is the same for all atoms of that element. In this lecture, we're going to talk about the mass of an atom and where the mass comes from. Atoms of one element differ in properties from atoms of all other elements. Those properties allow it to react in a different way. A compound consists of atoms of 2 or more elements combined in a small whole number ratio. In a given compound, the number of atoms of each of its elements are always present in the same ratio. Atoms are neither created nor destroyed during a chemical change, but instead rearranged to yield different types of matter. So this is just a close-up of copper, and copper is an element. It's made up of atoms of all the same type. The law of conservation of matter. So Dalton's atomic theory provides a microscopic explanation of the many macroscopic properties of matter that you've learned about. If atoms are neither created nor destroyed during a chemical change, then the total mass of matter present when matter changes from one type to another will remain constant. And that is the law of conservation of matter. So the mass of matter present when matter changes from one type to another doesn't change. So here's some starting materials and then the products. So starting materials are typically called the reactants. So you can see that the reactants recombine to create the products. Here you can see the starting materials recombining to create the products. There are 3 main components of an atom: protons, neutrons, and electrons. The atom is going to have a nucleus, and we'll learn a lot more detail about the nucleus, but within the nucleus of the atom, we're going to have subatomic particles called protons, and then we're going to have other subatomic particles called neutrons, and that makes the nucleus a dense center. Circulating around this nucleus, we have orbitals. And the orbitals are called electrons. So we can have electrons here, here, and they orbit around that central nucleus. If you think about our solar system, if you think the sun is at the center of the solar system, that's kind of like the nucleus of an atom. And then all the planets and everything circulates around the sun. So it all circulates around in orbitals. You've heard the Earth orbits the sun. I'm sure some of you say happy birthday by happy trip around the sun or that type of stuff. So you have these electrons that orbit around this nucleus. So protons are in the nucleus, and they have a positive charge. Neutrons are also in the nucleus, and they have a neutral charge. Electrons are found in orbitals. Orbitals are going to orbit or follow a circular path around the nucleus. Electrons have a negative charge. So protons positive, neutrons are neutral, and electrons have a negative charge. The nucleus contains the majority of an atom's mass. Protons and neutrons are much heavier than electrons. But electrons occupy almost all of an atom's volume. The diameter of an atom is about 10 to the negative 10 meters. The diameter of the nucleus is 100,000 times smaller. So this is a picture of a typical atom. So you can see the nucleus in the center, and then that cloud around there that's known as the orbitals or the electron cloud that surrounds it. And the electrons are in those orbitals that are within that cloud. They make up the majority of the size. So as a comparison, if the football field was the size of that electron cloud, or the size of the entire atom, the nucleus would be the size of about one blueberry. So if we put one blueberry in the center of a football field, that's about the relative size. Atoms and subatomic particles are very small. So for example, a carbon atom weighs less than 2 times 10 to the negative 23rd gram. Electrons have a charge of less than 2 times 10 to the negative 19. Small units are needed. An atomic mass unit, 1 AMU, is equal to 1.6605 times 10 to the negative 24 grams. So the mass of a carbon 12 atom is 12 AMU. We'll get into how we calculate masses and how we calculate the number of protons, neutrons, and electrons within atoms shortly. The fundamental unit of charge, E, is 1.602 times 10 to the negative 19. So protons have a mass of about 1.0073 AMU, and the charge is +1. Neutrons have the mass of 1.0087 AMU, slightly heavier than a proton, and a charge of 0. As I mentioned previously, neutral charge. Electron has a mass of 0.00055 AMU and a charge of about -1. So looking at this, you can see that this is about 1. This is about 1 AMU. And this is not even close to 1. So it's very, 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 very small. So when we start to calculate the number of protons and neutrons and electrons from the atomic mass and the atomic number, we typically consider electrons' mass to be negligible. So we don't include it in any of our calculations. The number of protons in the nucleus of an atom is known as its atomic number. So the atomic number is the number of protons in the nucleus of an atom. This is the defining trait of the element. Its value determines the identity of the atom. So however many protons are in the nucleus, that's how we know what atom we are working with. Next week's lecture content, we will get into a little bit more of how elements are arranged on the periodic table and how atoms within those elements are structured. So all of this stuff is really important to take notes on so that you know it for next week. For example, any atom that contains 6 protons is the element carbon and has the same atomic number, 6, regardless of how many neutrons or electrons it may have. A neutral atom must contain the same number of positive and negative charges. The number of protons equals the number of electrons. Therefore, the atomic number also indicates the number of electrons in a neutral atom. So if we think about hydrogen, hydrogen has 1 proton in the center. Hydrogen is also, to be neutral, is going to have 1 electron in the orbital. Because the electron has a negative charge, the proton has a positive charge, so -1 plus positive 1 gives us a neutral charge of 0. The total number of protons and neutrons in an atom is called its mass number. The number of neutrons is therefore the difference between the mass number and the atomic number. So the atomic number is just the number of protons. The mass number is the number of protons plus the number of neutrons. And if we subtract A minus C, the mass number minus the atomic number, we can calculate the number of neutrons. So the shorthand expression on the periodic table of elements, which we'll go through next week, every element has an element symbol. So this capital N happens to stand for nitrogen. And again, nitrogen is an element on the periodic table. Nitrogen, in shorthand expression, is going to have this smaller number here, which is the atomic number. It has a larger number up here, which is the mass number. And then it may or may not have a charge. So a charge is listed for this one, so that's how we see the charge there. So I'm going to go through the first one of how to calculate the number of protons, neutrons, and electrons. Then I'm going to ask you guys to work through the next two examples, and we'll go through it as a class. So this Na happens to be the chemical symbol for sodium. This, as you recall, is the atomic number, and this is the mass number. The atomic number is the number of protons in the nucleus of that atom. So there are 11 protons in the nucleus. As you can see here, there's no charge. So in an uncharged atom, the protons, the positive charges, have to equal the electrons, which are the negative charges. So however many protons we have to have the same number of electrons if there's no charge. So we're going to have 11 electrons. Now this mass number up here is equal to the number of protons plus neutrons that are found in the nucleus of the atom. So if we want to calculate the number of neutrons, we're going to take the mass number, 23, minus the atomic number, and that gives us the number of neutrons. So doing the math, we see we have 12 neutrons. So go ahead and pause the video and work through the next couple of problems to figure out the number of protons, neutrons, and electrons. And then you can unpause and we can go through them. Okay, so hopefully you had a chance to pause the video and work through the next few problems. So the number of protons, again, is going to be the atomic number. So for both of these, it's going to be, we got 15. And for this one down here, we have 8. The number of protons is also going to be equal to the number of electrons because there's no charge listed here. So we have 15 protons, which means we're going to have 15 electrons. Down here, there's no charge. We have 8 protons. That means we're going to have 8 electrons. Now to calculate the number of neutrons, you're going to take the big number minus the small number, the mass number minus the atomic number. So 31 minus 15 is going to give us 16. And 16 minus 8 is going to give us 8. Ions. So when the number of protons and electrons are not equal, the atom becomes electrically charged, and it's called an ion. The charge of an atom is equal to the number of protons minus the number of electrons. Atoms and molecules acquire charge by losing or gaining electrons. An atom that gains 1 or more electrons will exhibit a negative charge and is called an anion. For example, a neutral oxygen atom, Z equals 8, has 8 electrons, and if it gains 2 electrons, it will become an anion with a -2 charge. 8 minus 10 gives us a -2 charge. You might be wondering why the negative sign is after the number. In chemistry, that's how we dictate what charge something is. Because we don't want to say it's -2, because that indicates that it's a mathematical expression. When we give charges, we go 2 minus to indicate that it's a charge, and we're not actually subtracting 2 from something. So it's just a slight difference between actually addition and subtraction versus how you would depict a charge. Same thing at the bottom. When you have a +1 charge, we write that down as 1 plus, because we don't want people to assume that we're about to do a math problem. So, if we gain electrons, we're gaining negative charges. It actually decreases the charge by however many electrons we gain. So it's kind of a reverse way of thinking about things, and you really have to internalize this and wrap your head around the fact that when we're gaining electrons, we're gaining a negative charge. So when you're adding negatives, you're actually becoming more negative. When you're losing an electron, you're going to gain a positive charge because you're giving up negativity. You're becoming more positive. So if an atom has a negative charge, it's called an anion. And if it has a positive charge, it's called a cation. One way that I like to distinguish these are, I'm a crazy cat person. I have literally 6 cats in my house right now. Amongst other animals, I've got 4 dogs and all sorts of other critters. Cats are positive to me. So cation has a positive charge. Anion, if you think of like anarchy or an, when you put an in front of anything, it typically means like something negative or something bad or the absence of something. So anion is the negative charge. So it's one way to keep those two separate in your head. So this just shows one of the elements that can help. Insufficient iodine in the diet causes enlargement of the thyroid gland called a goiter. The addition of small amounts of iodine to salt prevents the formation of goiters and has helped to eliminate this concern in the United States where salt consumption is high. So every time you buy salt, you want to make sure it's iodized salt, and that will prevent thyroid deficiencies. A chemical symbol is an abbreviation that we use to indicate the element or an atom of that element. For example, the symbol for mercury is Hg. Some symbols are derived from the common name of the element, others are abbreviations of the name in another language. Most symbols have 1 or 2 letters, but 3-letter symbols have been used to describe some elements that have atomic numbers greater than 112. Only the first letter of a chemical symbol is capitalized. This is extremely important when you're writing chemical symbols. The answer will be marked wrong. You will get an incorrect answer if you don't put in the chemical symbol correctly. The first letter is capitalized. The second letter is lowercase. If there's only 1 letter, then that 1 letter is capitalized. So there will be some fill-in-the-blank questions on the upcoming module exam. So if you don't write them, they are case sensitive. So if you don't put them exactly correct, they'll be marked wrong. So you want to make sure that this point is very clear in your head. So the symbol Hg represents the element mercury. Regardless of the amount, it could represent 1 atom of mercury or a large amount of mercury. So this is just some common elements in their symbols. So aluminum is Al, bromine is Br, calcium Ca. There is a list that I would like you to have memorized. You don't have to memorize every symbol on the entire periodic table like I did way back when I took chemistry, but there are a few that are extremely relevant to the human body and to human health, and those are the ones that I want you to memorize. So with those, I'll give you a full list when we actually go through the periodic table of elements and I show you more of their details, and I'm going to describe a little bit more of why they're important, what they do to human health and in the human body, and we'll get a little bit more in detail once we get to that point. But for now, this is just showing you what some symbols look like. As you can see, every first letter is capital, and if there is a second letter, the second letter is lowercase. Isotopes. So iso means similar, something that you're going to learn in science. So whether you're taking an anatomy course, microbiology, any other field of science, genetics, most of these words are going to use common prefixes. And if you start to get to know what those prefixes are, you can actually break up the word into two separate parts, or three parts, or however many parts, and you can deduce the definition just by breaking apart the words. So isotope. Iso means similar. Tope is referring to a type of something. So they're similar types. So when we talk about a similar type of atom, an isotope is written by placing the mass number as a superscript to the left of the element symbol. The atomic number is sometimes written as a subscript to the left of the element symbol. For example, magnesium exists as a mixture of three isotopes, Mg24, Mg25, and Mg26. All isotopes have 12 protons, but the number of neutrons are different, and that's why they're called isotopes. They all have the same number of protons, but their number of neutrons is different. So that means that their mass number is going to be different. So same atomic number, different mass number. So here you can see the mass number, atomic number, and a charge of helium. And here you can see mass number, atomic number, and charge of magnesium. Hydrogen exists as a mixture of three isotopes. So there's H11, H21, and H31. This kind of got blurred together in the wrong table. It should be down here. Let me see if I can fix this real quick. There we go. So these are the three isotopes, and then when we start talking about atomic mass, mass number, we're taking an average of the isotopes. So most often it exists, so 99.989% of the time, it exists as H11, but there is a small amount of H21 and H31 that exist in nature. But when we do all of our assumptions about hydrogen, we're assuming it's one of the 99% most common form, or most common isotope. So each proton and neutron has a mass of about 1 AMU. Each electron weighs far less. Therefore, the atomic mass of a single atom, in AMU, is approximately equal to its mass number. However, most elements exist naturally as a mixture of two or more isotopes. So the periodic table lists the weighted average mass of all isotopes present in a naturally occurring sample of that element. So, atomic mass. Atomic mass is about equal, and when we use about equal, it's like a curvy equal sign, to the mass number. Remember, the mass number is the average mass of an atom. So we take the mass of the protons, the mass of the neutrons, mass of the electrons to get this mass number. The atomic mass is kind of rounded. So it's approximately equal to the mass number. The atomic mass gives us an average weight of the mass of all the isotopes present in a naturally occurring sample of that element. So this goes into a little bit more detail than what you're going to be expected to know in the class, but if you're interested in learning a little bit more about where the average mass comes from, We take the sum of the fractional abundance times the isotopic mass. So for example, the element boron is composed of two isotopes. About 19.9% is boron 10, and the other 80.1% is boron 11. And we average those masses based on the percentage that it exists in nature, and that's how we calculate the AMU. So the good thing about calculating AMUs in this class is all the information can be gathered from the periodic table.